What if everything you thought you knew about time was just the tip of the iceberg? Picture this. A second here on Earth might stretch into an eternity near a black hole, or vanish into a fleeting instant in the depths of space. Time isn't just a ticking clock, it's a cosmic enigma, bending and warping in ways that defy our everyday experience. From the moment we're born, we're taught that time moves forward, steady and unshakable. But out there in the universe, time dances to a different rhythm, one that'll leave you questioning reality itself. Think about the last time you stared at the night sky, wondering how far those twinkling lights had traveled to reach your eyes. Those stars aren't just distant suns, they're time machines. They're light carrying stories from billions of years ago. And here's the mind-blowing part. When you look up, you're literally peering into the past. But that's just the beginning. What if I told you that time can slow down or speed up depending on where you are in the universe, or that some places might exist where time doesn't flow at all? The deeper we dive into these mysteries, the more we realize how little we truly understand. That's why we're about to embark on a journey through 30 of the most astonishing facts about time in the cosmos, facts that'll twist your perception of reality like never before. We'll explore how black holes turn time into a rubber band, how relativity makes astronauts age slower than the rest of us, and how the universe itself might hold clues to time's ultimate secrets. This isn't just science fiction, it's the cutting edge of what we know and what we're still desperately trying to figure out. So buckle up, because by the end of this, you'll never look at a clock the same way again. Black holes don't just swallow light, they distort time itself. Imagine dangling a clock near the edge of one of these cosmic monsters. To you, watching from a safe distance, that clock would tick slower and slower, as if the hands were dragging through molasses. But for someone brave or foolish enough to ride that clock toward the black hole's abyss, time would feel perfectly normal. This bizarre effect isn't science fiction. It's one of the most jaw-dropping predictions of Einstein's theory of relativity. The stronger the gravity, the more time stretches and warps. Near a black hole where gravity is so intense that not even light can escape, time practically grinds to a halt from an outsider's perspective. Remember the scene in Interstellar where Matthew McConaughey's character spends what feels like minutes on a watery planet, only to return and find his daughter has aged decades. That's time dilation in action. The planet orbited a supermassive black hole, and its crushing gravity slowed time dramatically compared to Earth. While the movie took some creative liberties, the science behind it is shockingly real. Here's the kicker: this isn't just some far-off cosmic quirk. It affects us right here on Earth. GPS satellites orbiting our planet actually experience time slightly faster than we do on the ground because they're farther from Earth's gravity. If engineers didn't account for this, your navigation apps would be off by miles within minutes. So every time you use Google Maps, you're relying on Einstein's genius to keep you from getting lost. Black holes might seem like distant nightmares, but their shadow, the way they twist time, reaches further than you'd ever expect. Here's something that'll make your brain ache. The universe is 13.8 billion years old, yet it stretches 93 billion light years across. How can something grow so much larger than the time it's had to expand? The answer lies in one of the most mind-bending tricks of cosmology. Space itself is stretching, and it's doing so faster than light can travel through it. Picture the universe like a loaf of raisin bread baking in the oven. As the dough expands, every raisin moves away from every other raisin, not because they're traveling through the dough, but because the dough itself is swelling. Now replace the raisins with galaxies and the dough with space-time, and you've got cosmic expansion in action. This isn't just galaxies moving apart, it's the very fabric of reality growing between them. That's why light from galaxies near the edge of our observable universe, though emitted billions of years ago, still reaches us. The space those photons traveled through has stretched along the way, making their journey longer in distance but not in time from our perspective. The Hubble Ultra Deep Field Image, that famous speck of sky filled with thousands of galaxies, captures light that's been en route for over 13 billion years. Those galaxies are now far, far farther away than they were when their light first set out, all because space keeps stretching. But here's the real kicker: because expansion accelerates, some galaxies will eventually vanish from our view entirely. Their light, struggling against the relentless stretching of space, will never reach us again. We're left with a cosmic horizon, a limit to what we can ever observe, no matter how powerful our telescopes become. So when you hear the universe is 93 billion light-years wide, remember, it's not that stuff traveled that far. It's that space itself blew up like a balloon, carrying galaxies along for the ride. What if the past, present, and future aren't just moments slipping through our fingers, but fixed points, eternally locked in place like frames on a film reel? This is the spine-tingling idea behind the block universe theory, a concept that turns our everyday experience of time on its head. According to this view, every event from the birth of the cosmos to the moment you're hearing these words already exists in a vast, unchanging, four-dimensional tapestry. Think of it like a DVD. All the scenes are there at once, but your consciousness plays them one by one, creating the illusion of movement and change. Physicist Julian Barber takes this even further, arguing that time might not exist at all, it's just a trick of human perception. In his radical view, the universe is a collection of frozen moments like pages in a book, and our brains stitch them together into a story. Without memory, would we even notice time passing? Imagine waking up with no recollection of yesterday. Would you feel its absence, or would each moment feel like the only reality? This isn't just philosophical musing. Einstein's relativity already hints at this frozen cosmos. If you could hover outside the universe and look down, every collision of asteroids, every whispered conversation, every explosion of a star would appear as static as landmarks on a map. Your birth, your death, they'd all just be coordinates in space-time. Even stranger, from light's perspective, no time passes at all. A photon racing from a distant star to your eye experiences its entire journey instantaneously. So who's right, the photon, untouched by time, or us, trapped in its flow? The block universe might feel chilling, but it solves cosmic puzzles too. If the future's already out there, why can't we change it? Well, in this view, free will isn't about altering destiny. It's about discovering the path your life was always meant to take. Like reading a novel for the first time, the suspense is real, even if the ending's already written. So next time you glance at a clock, ask yourself, are you watching time pass or just flipping through pages in a book you can't put down? Hold onto your seats, because time travel isn't just for sci-fi movies. It's happening right now, and you could do it with the right technology. Here's how. If you hopped on a spaceship and zoomed through the cosmos at close to light speed, you'd return to Earth to find everyone older than you. Not by a little, by years. This isn't a theory. It's a direct consequence of Einstein's relativity, proven by countless experiments. The faster you move through space, the slower you move through time compared to those standing still. Take the famous twin paradox. Imagine one twin blasts off on a near light-speed journey while the other stays home. When the traveling twin returns, they might have aged only a few years, while their Earth-bound sibling could be decades older. This isn't hypothetical, it's baked into the fabric of reality. Even astronauts experience it on a tiny scale. After spending 340 days aboard the International Space Station, Scott Kelly was technically a fraction of a second younger than his identical twin brother Mark. Not exactly Back to the Future, but the principle is the same. Motion warps time. Now dial it up. Picture orbiting a black hole where gravity's grip is so fierce that time crawls. Spend an hour skirting its edge and decades could pass elsewhere. In Interstellar, Cooper's crew debates whether to land on Miller's planet, knowing the cost. Every hour there means 7 years lost on Earth. While the movie exaggerates the numbers, the science is shockingly sound. Black holes don't just bend light, they twist time into a pretzel. Here's the catch: you can only leap forward, never back. And you wouldn't feel time slowing down. Your watch would tick normally, but to everyone watching from Earth, you'd be moving in slow motion like a video stuck on buffering. The craziest part, we know this works. Particle accelerators fling tiny particles to near light speeds, and their lifespans stretch far beyond stationary ones. If we could build a ship that fast, humanity's first time travelers might not be magicians or mad scientists, just astronauts with really good engines. So next time you're stuck in traffic, remember, the highway to the future isn't a DeLorean, it's physics. Why does time only move forward? The answer might lie in something as simple as spilled milk, or more precisely, why it never jumps back into the glass. This irreversible flow is what physicists call the arrow of time, and it's governed by one of the universe's strictest laws: entropy always increases. Think of entropy as nature's obsession with messiness. A shattered vase, scattered papers, even the heat fading from your coffee. All these are examples of disorder creeping in, and the process only goes one way. You've never seen shards of glass leap off the floor and reassemble into a perfect cup because entropy forbids it. This isn't just about broken dishes. Entropy dictates the fate of the cosmos itself. Stars burn out, galaxies drift apart, and energy spreads thin, all because the universe is relentlessly marching toward maximum disorder. It's why we remember the past but not the future, why aging only moves in one direction, even why laughter fades in an empty room. Time's arrow isn't just a metaphor, it's baked into every atom. But what if the universe hit rewind? Some theories suggest a hypothetical big crunch, where the cosmos stops expanding and collapses back into a singularity. In that scenario, entropy might reverse, with chaos untangling into order as time flows backward. Imagine shattered glass piecing itself together, ashes reigniting into logs, or even memories unfolding in reverse. Though wildly speculative, this idea reveals how fragile time's direction might be. Here's the twist: even if the universe reversed course, we wouldn't notice. Our brains, bound by entropy's rules, would perceive the backward flow as normal. Like a movie played in reverse, every splash would look like droplets leaping into a pond, completely natural to observers living in that flipped reality. So next time you drop a plate, remember, its destruction isn't just a household accident. It's proof of time's relentless one-way march and the universe's ultimate expiration date. Here's something that sounds straight out of science fiction. Astronauts on the International Space Station are technically time travelers, not in the Doctor Who sense, but because they age slightly slower than the rest of us down here on Earth. Thanks to Einstein's general relativity, time doesn't tick at the same rate everywhere in the universe. The weaker gravity in orbit means clocks on the ISS run a tiny bit faster than those on the ground. Over a 6-month mission, an astronaut might gain about 0.007 seconds compared to people back home. That's not enough to notice, but it's proof that time is far more flexible than we ever imagined. This bizarre effect was first confirmed in the real world with the Hayfel-Keating experiment back in 1971. Scientists flew atomic clocks, the most precise timekeepers ever built, on commercial jets circling the globe. When they compared those clocks to ones left on the ground, the traveling clocks were ever so slightly behind. Not much, just a few hundred nanoseconds, but it matched Einstein's predictions perfectly. Gravity and motion both warp time, meaning the faster you go or the farther you are from Earth's pull, the more time bends in your favor. Now, here's where it gets wild. If you spent your entire life orbiting Earth like an astronaut, you'd technically outlive everyone on the planet by a fraction of a second. A space vacation won't make you immortal, but it would give you bragging rights at your high school reunion. Even crazier, GPS satellites have to account for this effect. Their clocks tick faster because they're farther from Earth's gravity. And if engineers didn't adjust for that, your phone's navigation would be off by miles within minutes. So every time you use Google Maps, you're relying on Einstein's math to keep you from getting lost, all because time itself isn't as constant as it seems. The takeaway: time isn't some universal metronome ticking the same for everyone. It's more like a river flowing at different speeds depending on where you stand. And if you ever find yourself complaining about time flying by, just remember, in space it literally does. The present moment, that fleeting now we all cling to, might be nothing more than an illusion. According to Einstein's relativity, what's happening right now for you could already be the past for someone else, or still the future for another. This mind-bending idea is called the relativity of simultaneity, and it shatters our everyday notion of a shared, universal present. To understand why, picture a train racing down the tracks at nearly the speed of light. At the exact instant the train's center passes a platform, two bolts of lightning strike, one at the front of the train, one at the back. For someone standing on the platform, both strikes happen simultaneously, but for a passenger sitting right in the middle of the train, the story's completely different. From their perspective, the lightning strike at the front happens first. Why? Because the train's moving so fast that light from the front strike reaches them before the light from the back strike can catch up. Same event, two different realities, one where the strikes are perfectly synchronized and another where they're not. This isn't a glitch in perception, it's a fundamental feature of the universe. Einstein himself put it best: the distinction between past, present, and future is only a stubbornly persistent illusion. Here's where it gets even stranger. Your now isn't just different from someone moving at high speed, it's also different depending on how far away you are. Light takes time to travel, so when you look at the sun, you're seeing it as it was 8 minutes ago. Glance at the star Alpha Centauri, you're peering 4 years into the past, and if you could somehow see a galaxy a billion light years away, your present would actually be their distant history. There's no cosmic clock ticking in unison across the universe, just a patchwork of overlapping moments, each valid for the observer experiencing them. This raises a haunting question. If the present isn't universal, does it even exist? Some physicists argue that now is just a trick of the brain, a way for our minds to make sense of a reality where time is far more fluid than we realize. Think of it like frames in a film strip. The movie exists all at once, but we only experience one frame at a time, creating the illusion of motion. Could time be the same? A fixed tapestry where our consciousness slides along, stitching together what we call the present. The implications are staggering. It means two people could genuinely disagree about whether an event has already happened or is yet to come, and both would be right. A supernova exploding in a distant galaxy might be ancient history for Earth astronomers, but for aliens racing toward us at near light speed, it could still be a future waiting to unfold. There's no privileged now, no master timeline, just a universe where time is as personal as a fingerprint, and the present is wherever you happen to be standing. We've been taught that time began with the Big Bang, that cosmic moment when the universe exploded into existence 13.8 billion years ago. But what if time didn't start there? What if the Big Bang wasn't the beginning, but just another chapter in an endless cycle of creation and destruction? Some of the boldest theories in physics suggest exactly that. Take loop quantum gravity, for instance. This framework imagines the universe not as a one-time explosion, but as a cosmic accordion, expanding and contracting over and over. In this view, our Big Bang might have been the rebound of a previous collapse, a big bounce, where time didn't begin but simply switched direction, like a pendulum swinging back. Then there's Stephen Hawking's no-boundary proposal, a concept so radical it redefines what before even means. Hawking suggested that at the Big Bang singularity, time itself morphs into something akin to space. Picture standing at the North Pole. No matter which way you face, every direction is south. Similarly, at the birth of the universe, there's no before, because time loses its usual meaning and curves into a dimension more like space. Asking what happened before the Big Bang becomes as nonsensical as asking what's north of the North Pole. But the wildest part, these ideas aren't just speculation, they're backed by serious math. Loop quantum gravity, for example, replaces the Big Bang's infinite density with a quantum fuzz, a state so dense yet finite that time could have flowed right through it. Imagine the universe as a movie reel. We've always assumed the film starts with our Big Bang, but what if there are scenes, entire plot lines hidden on the other side of the celluloid? The implications are staggering. If time existed before the Big Bang, our universe might be one in an endless series, each with its own laws of physics, its own stars and galaxies, even its own versions of us. And if Hawking was right, the very question of a beginning might be a trick of human intuition, like a fish trying to imagine life outside water. So next time someone says everything started with the Big Bang, remember, the cosmos might have been ticking long before that, or maybe, just maybe, time never started at all. Imagine a clock that keeps perfect time forever without ever needing to be wound. No springs, no batteries, just an endless, unchanging rhythm built into the very fabric of matter. This isn't a fantasy, it's the bizarre reality of time crystals, a phase of matter so strange it defies our most basic assumptions about physics. Unlike ordinary crystals, like diamonds or snowflakes, which repeat their atomic patterns in space, time crystals repeat their structure in time, ticking like a metronome without any energy input. Think of them as the universe's heartbeat, a pulse that never fades. The idea was first proposed by Nobel laureate Frank Wilczek in 2012, but many physicists dismissed it as impossible. How could something oscillate indefinitely without violating the laws of thermodynamics? Then, in 2017, two separate teams, one at Harvard, another at the University of Maryland, actually built time crystals using chains of ytterbium ions and diamond impurities. Their secret, quantum entanglement, the same spooky connection that allows particles to influence each other instantly across vast distances. By nudging these systems with a laser pulse, researchers coaxed them into a state where their atoms flipped back and forth in a never-ending dance, like a pendulum that swings forever without friction. Here's what makes time crystals truly revolutionary. They're the first objects ever discovered that break time symmetry. Normally, the laws of physics work the same whether time runs forward or backward. Drop a ball, and the motion looks sensible in reverse. But time crystals are different. Their rhythmic patterns only make sense in one direction, marking an arrow of time baked into their structure. It's as if you filmed a clock's gears turning, then played the tape backward and realized the teeth no longer fit together. So what could we do with these cosmic curiosities? Quantum computing is the most tantalizing possibility. Today's quantum bits or qubits are notoriously fragile, collapsing at the slightest disturbance. But time crystals, with their inherent stability, might serve as perfect quantum memory, preserving information against decoherence like a fly trapped in amber. Some theorists even speculate they could help build fault-tolerant quantum computers, machines so precise they'd outpace conventional supercomputers for certain tasks. And then there's the existential wonder of it all. Time crystals hint at a deeper truth. The universe might be filled with hidden rhythms, structures that endure not just across space but across time itself. Maybe black holes pulse with unseen frequencies, or dark matter hums in crystalline patterns we can't yet detect. One thing's certain, if time crystals teach us anything, it's that time isn't just something we measure. It's something matter can embody, a beat that never fades, even in the silence of empty space. If you think a nanosecond is fast, wait until you meet the universe's ultimate stopwatch, Planck time. Lasting just 10 to the power of -43 seconds, this is the smallest possible slice of reality, a blink so brief that light barely crosses a single Planck length in that instant. Below this, physics as we know it collapses into chaos. It's not that we lack the technology to measure shorter intervals, it's that time itself loses all meaning. At this unimaginable scale, spacetime isn't smooth and predictable like Einstein envisioned. Instead, it becomes a seething quantum foam, a turbulent sea where tiny bubbles of energy flicker in and out of existence. Virtual particles pop up like cosmic static, borrowing energy from the vacuum before vanishing again. Gravity, usually the quiet architect of orbits and galaxies, becomes so violent that it warps the very fabric of reality into knots. Here, the orderly rules of relativity and quantum mechanics tear at each other like rival forces, leaving scientists with equations that spit out infinities, a sure sign we're missing something fundamental. Why can't we go smaller? Think of Planck time as the universe's pixel size. Just as blurring a photo reveals individual dots, zooming into spacetime beyond this limit shows only chaos, like trying to read a book shredded into confetti. Even the most precise clocks, like atomic timekeepers or pulsars, are lumbering giants compared to this quantum heartbeat. The wildest implication: if you could witness Planck time, you'd see a reality where cause and effect unravel. Events might happen in reverse or simultaneously, with particles teleporting unpredictably. It's a realm where the very ideas of before and after dissolve, a place so alien that calling it time almost feels wrong. This isn't just theoretical trivia. Planck time holds the key to unlocking quantum gravity, the holy grail of physics. If we ever crack how spacetime behaves at this scale, we might finally reconcile Einstein's cosmos with the bizarre rules of the quantum world. Until then, Planck time remains the ultimate frontier, a stop sign at the edge of known physics, whispering that beyond it lies either nonsense or revolution. Here's something you might not expect. Your head ages faster than your feet, not by much, just a fraction of a second over an entire lifetime. But it's real and it's happening right now. This bizarre effect isn't science fiction, it's a direct consequence of Einstein's general relativity. The closer you are to Earth's core, the stronger gravity's grip and the slower time ticks. That means someone living at sea level actually experiences time slightly slower than someone on a mountaintop. Scientists proved this in a groundbreaking 2010 experiment using the world's most precise atomic clocks. They placed one clock at the National Institute of Standards and Technology in Colorado, about 1,600 meters above sea level, and another at the University of Colorado in Boulder, just 33 centimeters lower in elevation. After a year, the higher clock had ticked faster by about 15 nanoseconds. That's less time than it takes light to travel the length of a school bus, but the implications are staggering. Gravity doesn't just bend space, it bends time itself right here on Earth. Now picture this: if you spent your entire life living on the top floor of a skyscraper, you'd technically age a few microseconds more than your neighbor on the ground floor. Over 80 years, the difference adds up to roughly 90 microseconds, barely enough to notice, but proof that time isn't as rigid as it feels. Even GPS satellites have to account for this effect. Orbiting 20,000 kilometers above Earth, their clocks tick about 45 microseconds faster each day than ground-based ones. Without correcting for relativity, your phone's navigation would be off by nearly 10 kilometers within minutes. But here's the real kicker: this isn't just about clocks. Your biological aging is subject to the same rules. Atoms in your cells vibrate slightly slower at sea level than they would in the Himalayas, meaning someone living high in the Andes literally ages a tiny bit faster than someone in a coastal city. It's not enough to add wrinkles or gray hairs prematurely, but it reveals something profound. Time isn't just something we measure. It's woven into the fabric of our bodies, changing ever so slightly with every step we take up or down. So next time you're hiking a mountain, remember, with every meter you climb, you're not just gaining altitude. You're stepping into a part of the world where time itself runs just a little quicker, a hidden whisper of relativity ticking away beneath your feet. What if every choice you've ever made and every choice you didn't make is playing out right now in some alternate reality? Welcome to the multiverse, a mind-bending concept where our universe isn't alone but just one bubble in an infinite cosmic foam of parallel worlds. This isn't just wild speculation. It's a serious scientific idea called eternal inflation, where space expands so rapidly that new universes constantly bud off like bubbles in a boiling pot. Each of these universes could have completely different laws of physics. Some might have stronger gravity, others might have no stars at all, and a few might even contain doppelgangers of you living out every possible version of your life. The implications are staggering. Take Schrödinger's famous cat trapped in a box where it's both alive and dead until someone looks inside. Quantum mechanics says particles exist in multiple states until observed, but the many worlds interpretation takes this further. Instead of the cat's fate resolving into one outcome, the universe splits: one timeline where the cat survives, another where it doesn't. Every quantum event, no matter how tiny, could spawn new branches of reality. Did you turn left at the intersection this morning? Somewhere out there, a version of you turned right, and their life might now be radically different. But here's the real kicker. If the multiverse is infinite, then every possible timeline must exist. There's a universe where dinosaurs never went extinct, one where you're a famous artist, another where Earth never formed at all. Even the most improbable events, like a room full of monkeys randomly typing Shakespeare, become inevitable given enough parallel worlds. The catch: we'll likely never meet these alternate selves. Each universe is sealed off, its existence implied by math rather than direct observation. This raises a haunting question. Does free will mean anything if every choice plays out somewhere? Physicists are split. Some argue that all versions are equally real, making life a choose-your-own-adventure book where you experience just one path. Others insist that branching timelines don't diminish your agency, they just reflect the staggering complexity of quantum possibility. Either way, the multiverse forces us to rethink what reality even means. So next time you hesitate over a decision, remember, in some distant corner of the cosmos, another you might already know how it plays out, but in this universe, the story's still yours to write. Here's a fact that'll bend your brain. If you could hitch a ride on a photon, a particle of light, your journey across the entire universe would feel instantaneous. No hours, no minutes, not even a fraction of a second. From the photon's perspective, time doesn't just slow down, it stops completely. This isn't some poetic metaphor, it's one of the most startling predictions of Einstein's relativity. Light doesn't experience time because at light speed, the very concept of duration ceases to exist. Think about it this way. When you turn on a flashlight, those photons race away at 300,000 kilometers per second. From your point of view, it takes 8 minutes for sunlight to reach Earth, or 2.5 million years for light from the Andromeda galaxy to hit your eyes. But for the photons themselves, the trip feels like a single, frozen moment. It's as if you blinked out of existence at the moment of creation and reappeared at your destination with no time passing in between. This bizarre reality explains why nothing can travel faster than light. Speed isn't just about distance covered, it's about how much you're trading space for time. As an object accelerates, time for it slows down relative to the outside world. Hit 99.9% of light speed, and clocks aboard your ship would crawl to a near standstill. But reaching 100%, that's the edge of the cosmic speed limit where time flatlines entirely. If you somehow exceeded light speed, the math suggests you'd start moving backward through time. Your arrival would happen before your departure, violating causality itself. The universe enforces this rule ruthlessly. Particles with mass can never reach light speed because doing so would require infinite energy. It's like running on a treadmill that speeds up. The harder you push, the closer you get to the limit, the more energy you need, with no way to cross the finish line. Even massless particles like photons pay a price. Trapped in a perpetual now, they're denied any experience of time's flow. But here's the twist: this law isn't just some arbitrary cosmic rule. It's woven into the fabric of space-time to preserve the order of cause and effect. If you could outpace light, you could theoretically send a message to your past self, creating paradoxes where events precede their own causes. Imagine hearing the echo of a shout before you ever opened your mouth. It's not just impossible, it's nonsensical. The universe's speed limit isn't just about physics, it's about keeping reality logically consistent. So next time you see a beam of light, remember, that photon isn't just moving through space. It's frozen in a timeless state, a fleeting messenger from a realm where the clock never ticks, and where breaking the speed limit doesn't just earn you a ticket, it unravels the very fabric of time itself. One of the most chilling predictions in cosmology isn't about how the universe began, but how it might end. Picture this: trillions of years from now, the last star flickers out, black holes evaporate into whispers of radiation, and the cosmos becomes an endless, featureless void where not even atoms move. This slow, silent fade into darkness is called heat death, and it's the universe's most likely expiration date. The culprit, entropy, the same force that makes your coffee cool and broken glass refuse to reassemble, will eventually max out, leaving no energy left to power anything, anywhere. Time in this frozen graveyard would lose all meaning. Without change, without events, there's nothing to measure. Just an infinite stretch of sameness where before and after are indistinguishable. But heat death isn't the only apocalyptic scenario lurking in the equations. There's a far more violent possibility: the Big Rip. Imagine dark energy, the mysterious force accelerating cosmic expansion, growing stronger over time. Instead of gently pushing galaxies apart, it could eventually overpower every force in nature. First, galaxy clusters would tear away from each other. Then, individual galaxies would unravel, stars would be ripped from their orbits, planets shredded. Even atoms, the building blocks of matter, would be pulled apart, their nuclei unable to withstand the relentless stretching of space itself. The universe wouldn't just die, it would be dismantled piece by piece, down to the smallest particles in a final cataclysmic instant. Here's the terrifying twist: we don't know which fate awaits us. Heat death assumes entropy wins while dark energy stays constant. The Big Rip requires dark energy to intensify unpredictably. There's even a third option: the Big Crunch, where expansion reverses and the universe collapses back into a singularity, possibly rebooting the cosmos in a new Big Bang. Each scenario hinges on mysteries we've yet to solve: the true nature of dark energy, the ultimate behavior of entropy, even whether our universe is one bubble in an infinite multiverse with its own unique rules. These aren't just abstract doomsdays, they shape how we understand time's arrow. Heat death suggests time's flow depends on change, no time. The Big Rip implies time could end abruptly, like a movie reel snapping, and the Big Crunch, it hints at a cyclical universe where time might loop eternally. For now, all we can do is watch the clues: how fast galaxies recede, how dark energy behaves, and listen to the whispers of a cosmos that's already counting down to its final act. What if you could step through a cosmic shortcut and emerge not just on the other side of the galaxy, but in an entirely different era? Wormholes, those famous sci-fi tunnels through space-time, might not just connect distant places. According to Einstein's equations, they could bridge times too, turning a journey across the cosmos into a one-way trip to the past or future. The math behind this is wild but shockingly real. Picture space-time as a folded piece of paper with two distant points pressed together. A wormhole is like poking a pencil through the fold, creating a bridge that bypasses the usual route. And here's the twist: if one end of the wormhole gets hurled near the speed of light or parked near a black hole, time would slow down there relative to the other end. Step through the right way and you might exit years before you even left. The catch: wormholes are ridiculously unstable. Without some cosmic duct tape, they'd snap shut faster than you could say paradox. That's where Kip Thorne, the physicist behind interstellar science, comes in. His calculations showed that keeping a wormhole open would require something called exotic matter, a hypothetical substance with negative energy that could prop the tunnel open like scaffolding. Think of it as anti-gravity glue, counteracting the natural tendency of spacetime to collapse. The problem: exotic matter might not even exist, or if it does, we'd need amounts far beyond anything we've ever detected. Now for the fun part, the grandfather paradox. Say you zip back in time and accidentally prevent your own birth. How could you exist to make the trip in the first place? Physics has a few cheeky answers. Maybe the universe enforces consistency like a bouncer at a club, only letting timelines that don't contradict themselves. Or perhaps every jump spawns a parallel universe, letting you shove your ancestor off a cliff in some reality without erasing yourself in this one. The wildest idea. Wormholes might already exist, woven into the quantum foam of spacetime at scales too tiny to see. If we could somehow enlarge one and dodge the paradoxes, it wouldn't just revolutionize travel. It'd make time itself a playground. Until then, we're stuck with the ultimate cosmic tease. The math says it's possible, but the universe seems hell-bent on hiding the keys. Even in the smallest corners of the universe, time plays tricks that seem impossible, like particles teleporting through solid walls or vanishing into thin air. This isn't magic, it's quantum tunneling, one of physics' most baffling phenomena. Picture a ball rolling up a hill. Classically, it needs enough energy to reach the top or it rolls back. But in the quantum world, that ball might suddenly appear on the other side of the hill without ever climbing it, as if it blinked out of existence and rematerialized past the barrier. How, at the subatomic level, particles don't behave like tiny marbles. They're more like ghostly probability waves existing in multiple states until observed. There's always a minuscule chance, governed by quantum weirdness, that a particle will tunnel through an obstacle it shouldn't have the energy to cross. It's not that the particle smashes through, it's as if the barrier briefly disappears for it. This happens constantly inside stars, where tunneling lets hydrogen nuclei fuse despite mutual repulsion. Without it, the sun wouldn't shine. Now here's where it gets wild. Some theories suggest tunneling might not just leap across space but time. In radioactive decay, an atom's nucleus spontaneously ejects particles, seemingly deciding at random when to implode. But what if that decay isn't random? Hypothetically, a particle could tunnel backward in time, influencing its own decay before the event even occurs. It's like a billiard ball sinking into a pocket, then reappearing on the table a second before it was struck, a paradox that makes physicists shudder. This isn't just microscopic trivia. If quantum effects could scale up like in The Prestige, where a magician's teleportation act hinges on a fictionalized version of tunneling, could we leap through time? The odds are vanishingly slim. For a person to tunnel, every particle in their body would need to synchronize this improbable jump, an event so unlikely it'd take longer than the universe's lifespan to happen once. But the mere possibility reveals time's flimsy grip at quantum scales, where cause and effect blur into a haze of maybes. So next time you hear about radioactive decay or stare at the sun, remember, beneath the surface, particles are playing hopscotch with reality itself, cheating barriers in ways that make time look like a suggestion, not a rule. For thousands of years, humans have wrestled with a problem that seems simple on the surface: how to neatly slice time into manageable chunks. Our modern Gregorian calendar, with its uneven months and leap year adjustments, is actually a messy compromise, one that ancient civilizations and even modern thinkers have tried to fix. Enter the 13-month calendar, a radical yet elegant solution that aligns perfectly with natural cycles. Instead of 12 mismatched months, this system divides the year into 13 equal periods of 28 days each, mirroring the moon's phases with uncanny precision. Each month would start on a new moon and end on a full moon, syncing our schedules with the celestial rhythms that once guided early farmers, hunters, and sailors. This idea isn't new. The Mayans, whose astronomical observations were centuries ahead of their time, used a 13-month lunar calendar alongside their solar tracking. Even today, indigenous cultures from the Andes to Polynesia still honor lunar cycles in their traditional timekeeping. But in the 1940s, an American businessman named Moses Cotsworth pushed the concept further, proposing the International Fixed Calendar. His version included a 13th month called Sol, sandwiched between June and July, with every month spanning exactly 4 weeks. Birthdays would always fall on the same day of the week, holidays would stay fixed, and businesses could compare monthly reports without seasonal distortions. So why did we stick with the Gregorian chaos? The answer lies in inertia and tradition. When Pope Gregory XIII introduced his calendar in 1582, it wasn't about harmony with nature, it was about fixing Easter's drift away from the spring equinox. The Church prioritized religious synchronicity over lunar cycles, and the system stuck. By the time Cotsworth and others proposed reforms, the Gregorian calendar was already deeply embedded in global trade, law, and culture. Imagine reprogramming every computer, rewriting every contract, and retraining billions of people. It's a logistical nightmare that outweighs the benefits of cosmic alignment. Yet the flaws in our current system are hard to ignore. February's 28-day shortness, July and August's back-to-back 31-day sprawl, none of it reflects astronomical reality. Meanwhile, the 13-month calendar smooths out these quirks, offering a symmetrical year where each quarter matches perfectly. No more scrambling to remember which months have 30 days or worrying about payroll discrepancies. Even farmers could benefit, as planting and harvest cycles would align more closely with lunar phases, something many agricultural societies still swear by today. The resistance to change reveals something deeper about how humans relate to time. We've prioritized political and religious convenience over natural harmony, bending the cosmos to fit our paperwork rather than the other way around. But every time you jot down a date or miss a meeting because time got away from you, remember, there was another path, one where the moon's gentle rhythm guided our days, and the year unfolded in perfect, equal slices, no leap years required. Ever feel like time flies when you're having fun? For a housefly, every moment feels like it's crawling by in slow motion. That's because their tiny brains process information at lightning speed, perceiving the world at a rate that would leave us dizzy. Scientists measure this using something called the flicker fusion rate, the speed at which flashing lights appear to merge into a steady glow. For humans, it's around 60 flashes per second. But for a fly, up to 250 to them. A slap in midair doesn't come out of nowhere, it unfolds like a slow-motion action scene, giving them plenty of time to dodge. This supercharged perception isn't just about reflexes, it's a survival tool honed by evolution. Faster metabolism means faster neural processing, and small creatures like hummingbirds or mice live in a sped-up world where every millisecond counts. Imagine watching a movie where everyone moves like they're stuck in molasses. That's reality for a fly. Even something as simple as a rolling raindrop becomes a life or death obstacle course when you experience time at that resolution. Now shift gears to an elephant. These gentle giants operate on the opposite end of the spectrum. With slower metabolisms and longer lifespans, their perception of time is far more languid. Their flicker fusion rate dips as low as 10 flashes per second, meaning rapid movements blur together into a smooth flow. A human waving a hand might appear as a faint smear to an elephant, while the fly sees each individual finger twitch. This isn't just a curiosity, it's an adaptation to their environment. Elephants don't need to dodge predators at breakneck speeds. Their world revolves around patient foraging, long migrations, and social bonds that unfold over decades. The kicker, this isn't just about biology, it reshapes how different species experience reality itself. A second for a mayfly, which lives just 24 hours as an adult, might feel as packed with activity as an entire human year. Meanwhile, a Galapagos tortoise clocking in at over a century of life perceives time's passage so slowly that seasons might blur like passing clouds. So next time you swat at a mosquito or watch an elephant lumber across the savannah, remember, you're not just seeing another creature, you're glimpsing a completely different rhythm of existence where time itself stretches or compresses to fit the needs of life. Physics has an embarrassing secret. It can't define what now actually means. Think about that for a second. We've charted the birth of stars, glimpsed particles blinking in and out of existence, even predicted how time bends near black holes. Yet the very moment you're experiencing as this instant, science has no official consensus on what that is. At the heart of this mystery lies a fierce battle between two philosophies, presentism and eternalism. Presentism argues that only the present moment is real. The past is gone, the future unwritten, like a spotlight moving across the timeline of reality. Eternalism, on the other hand, claims past, present, and future all exist equally, fixed in space-time like frames in a film reel. Einstein himself leaned toward eternalism, declaring the distinction between past, present, and future is only a stubbornly persistent illusion. But quantum mechanics throws gasoline on this fire. In the quantum world, particles don't settle into definite states until measured a phenomenon called superposition. Until you look, an electron might spin both clockwise and counterclockwise simultaneously. This raises a bizarre question. If reality at the smallest scales remains unresolved until observation, can there truly be a universal now? Some interpretations suggest quantum events don't happen until they interact with a conscious observer, meaning your present might not align with someone else's on the other side of the universe. The problem gets even thornier when relativity enters the mix. Imagine two astronauts passing each other at near light speed. For one, a supernova explodes now. For the other, watching from their high-speed ship, that same explosion might still be centuries away. Neither is wrong. Relativity insists both perspectives are equally valid. This shatters any hope of a cosmic clock synchronizing the universe. Even Earth isn't immune. A clock on a mountaintop ticks imperceptibly faster than one in a valley due to gravity's grip, meaning two people standing at different altitudes experience slightly different nows. So where does this leave us? Some physicists argue time itself might be emergent, a side effect of deeper quantum processes like temperature arising from atomic motion. Others propose that consciousness stitches together the illusion of a flowing present from disjointed quantum moments. One thing's certain, the harder we stare at the concept of now, the more it slips through our fingers, leaving us to wonder whether the present is a fundamental truth or just a trick our brains play to make sense of a far stranger reality. What if the smooth flow of time you're experiencing right now is just an elaborate illusion, a trick your brain plays to make sense of a reality that's actually a series of disconnected snapshots? This unsettling idea lies at the heart of the species present, a theory suggesting our conscious experience isn't a continuous stream but a carefully constructed montage of discrete moments, stitched together like frames in a film reel. Your brain doesn't process the world in real time. It works on a slight delay, collecting sensory data, editing out blinks and gaps, then presenting you with a polished version of events you've already lived through. Experiments reveal just how fragile this illusion really be. In one study, participants wore headphones playing a tone in one ear slightly before the other, yet they perceived the sounds as simultaneous. Their brains retroactively adjusted their perception to create coherence, effectively rewriting history to match expectations. Even more jarring, if you touch your nose and toe at the same instant, you'd swear the toe sensation came later, because the signal takes milliseconds longer to travel up your legs. Yet your brain edits the timeline, making both touches feel synchronized. Neuroscientist David Eagleman demonstrated this with a shocking twist. Volunteers wore a device that flashed a light while delivering a delayed tap to their finger. After a few repetitions, their brains compressed the delay until eventually they felt the tap the instant they saw the flash, even when it arrived late. The conclusion: consciousness isn't a live broadcast, it's more like a director's cut, where your brain smooths over inconsistencies and adds sound effects after the fact. This raises a profound question. If our perception of time is just a best guess reconstruction, what else might we be missing? Some theorists suggest quantum processes in the brain could create tiny gaps in consciousness, micro-moments where reality flickers in and out like a faulty light bulb. We'd never notice because our brains fill the void seamlessly. Even stranger, disorders like a kinetic mutism show what happens when this stitching fails. Patients become stuck in disconnected moments, unable to string thoughts together into a narrative, living proof that time's flow in our minds is more fragile than we ever imagined. So the next time you feel immersed in the present, remember, you're not experiencing now as it happens. You're watching a carefully edited highlights reel, one where your brain holds the scissors. If you think jet lag is bad after crossing a few time zones, imagine traveling across the galaxy. Near the Milky Way's supermassive black hole, Sagittarius A, time crawls so slowly that an alien civilization there could still be watching the dinosaurs roam Earth, while beings on the galactic outskirts have already evolved into post-singularity intelligences. This isn't just speculative fiction, it's the brutal reality of gravity's grip on time. Einstein's relativity tells us that clocks tick slower in stronger gravitational fields, meaning a galactic time zone near the core would diverge wildly from one in the sparse outer arms. Picture the world of Avatar, where humans mine the fictional moon Pandora. If that moon orbited close to Sagittarius A, the time dilation would make Interstellar look tame. A single work shift for a miner near the black hole could span decades back on Earth. Miss a single family call, and you'd return to find your grandchildren older than you. The math behind this is staggering. At just one astronomical unit from Sagittarius A, Earth's distance from our Sun, time would slow by roughly 34%. Spend 5 years there, and nearly 8 would pass in the outer galaxy. But here's the twist: even without black holes, the Milky Way's sheer mass warps time. Stars orbiting closer to the galactic center, where billions of suns crammed together, experience subtly slower time than those in the lonely spiral arms. Over billions of years, this adds up. Civilizations born in dense star clusters might evolve on a slightly decelerated timeline compared to their outer disk neighbors. It's as if the galaxy itself has built-in time zones, invisible but inescapable. Now, consider the implications for alien contact. If advanced life exists near the core, their signals reaching us would be stretched and slowed like a record playing at the wrong speed. A message that took 10,000 years to travel might encode 50,000 years of their history compressed into our faster-flowing time. Even stranger, their telescopes would see our region of the galaxy speedrunning through time, stars flaring and dying like hyperlapse footage. The craziest part, we're already living in a mild cosmic time zone. Earth's position in the Milky Way's mid-range suburbs means our clocks strike a balance: not too fast, not too slow, but venture deeper toward the glowing core, and time itself becomes a currency, trading at different rates across the galaxy. So next time you check your watch, remember, somewhere out there, an alien might be glancing at theirs, utterly unaware that their now is your distant past or future. In the 4th century, the philosopher St. Augustine wrestled with a question that still stumps us today. What was happening before time began? He framed it in theological terms. What was God doing before creation? But stripped of religious context, the puzzle remains just as baffling. Modern cosmology gives us a version of Augustine's dilemma. If time itself began with the Big Bang, then asking what came before is like asking what's north of the North Pole. The question doesn't just lack an answer, it might not even make sense. To grasp why, picture spacetime as a tapestry woven at the moment of the Big Bang. Before that instant, there was no before, because time didn't exist to measure it. It's not that the universe sprang from nothingness in the way we typically imagine, a blank canvas suddenly painted. Instead, the very concepts of nothing and suddenly rely on time which hadn't yet emerged. Think of it like a movie reel. If you splice out the first frame, there's no earlier scene to reference. The Big Bang isn't an event in time, it's the origin of time itself. This doesn't stop physicists from speculating, of course. Some theories, like loop quantum gravity, propose that our Big Bang was a rebound from a previous universe's collapse, a cosmic bounce where time flipped direction but never truly began or ended. Others, like string theory, suggest our universe might be one bubble in an eternal multiverse, where time flows differently in each pocket. But even these ideas run into the same existential wall. If time is intrinsic to a universe, then speaking of before that universe is like describing the taste of a color, a category error. The human brain isn't wired to comprehend this. We're prisoners of causality, trained to think in terms of sequence, first this, then that. But at the scales where space-time itself is born, our intuition fails. Consider a black hole singularity, a point where gravity crushes matter so densely that time and space cease to function. We can't peer inside because the laws of physics as we know them break down. The Big Bang singularity is even more extreme, not just a point in space, but the birth of space and time together. Asking what preceded it is like demanding to see the back of a one-sided coin. Yet the mystery doesn't end there. Quantum mechanics hints that true nothingness might be unstable, a seething foam of potential universes bubbling in and out of existence, with ours just one that stuck. In this view, time's beginning might not be a hard boundary, but a transition from chaos to order, like ice crystallizing from water. But without time to mark the process, how could such a transition even occur? The more we probe, the clearer it becomes. Time's origin isn't just a scientific question. It's a philosophical earthquake shaking our deepest assumptions about reality. So next time you catch yourself wondering what came before, remember, the answer might not be hidden in some distant past, but in the realization that the question itself is a mirage, one that evaporates when we stare too closely. Time doesn't just shape our universe, it defines what a universe even is. What if everything you perceive, every ticking second, every stretch of space-time, even your own thoughts, was nothing more than a cosmic mirage? This isn't the plot of a sci-fi movie. It's the radical idea at the heart of the holographic principle, a theory so mind-bending it suggests our three-dimensional universe, complete with the illusion of time, might be a projection of information encoded on a distant two-dimensional surface. Think of it like a bank hologram on a credit card. The shimmering 3D eagle isn't really there, it's just light reconstructing data etched onto a flat plastic strip. Now imagine that trick scaled up to galactic proportions, with the entire cosmos as the illusion and the edge of the observable universe as the plastic strip. The roots of this idea trace back to an unexpected place: black hole thermodynamics. In the 1970s, physicist Jacob Bekenstein discovered something astonishing. Black holes have entropy, a measure of disorder typically tied to heat and information. Even stranger, that entropy isn't proportional to the black hole's volume, as you'd expect for a three-dimensional object, but to its surface area. It's as if all the information about what fell into the black hole wasn't stored inside but smeared across its event horizon like invisible ink. This realization led Gerard T. Hooft and Leonard Susskind to propose the holographic principle. Perhaps all the information in our universe, from the spin of electrons to the memories in your brain, is similarly encoded on a boundary far away, a cosmic hard drive operating in fewer dimensions than we experience. Here's where time gets warped. In this holographic view, time as we know it might not be fundamental. Just as a movie on a flat DVD produces the illusion of motion when played, the flow of time could emerge from how this lower dimensional data is projected into our 3D reality. Picture a flipbook. Each page is static, but flipping through them creates the sensation of movement. Similarly, our experience of past, present, and future might just be the universe's way of reading the hologram. The implications are staggering. If the holographic principle holds, then black holes aren't just cosmic vacuum cleaners, they're Rosetta Stones for decoding reality itself. Their event horizons might be the pixels of the universe's true, lower-resolution screen. Even stranger, this could solve physics' biggest headache, uniting Einstein's smooth spacetime with the chaotic quantum world. On the 2D boundary, quantum mechanics reigns. In our 3D projection, relativity takes over. The holographic principle might be the bridge between them. But how do we test something so abstract? Enter quantum entanglement, that spooky link between particles. Experiments with entangled particles suggest space might be built from these connections, just like a 3D image emerges from 2D data. And in 2022, physicists used quantum processors to simulate a holographic universe, finding patterns that matched predictions, tiny clues that we might all be living inside a cosmic hologram. So next time you check your watch, consider this. The seconds ticking away might not be real in the way you think. They could be shadows, artifacts of a deeper, weirder reality where time isn't flowing but flashing, frame by frame, from a dimension we can't even see. What if staring at something hard enough could literally freeze it in time? That's exactly what happens in the quantum world, where the simple act of observation doesn't just measure reality, it changes it. This bizarre phenomenon is called the quantum Zeno effect, named after an ancient Greek philosopher's paradox about motion. Imagine an arrow shot toward a target. Zeno argued that before reaching the target, the arrow must first cover half the distance, then half the remaining distance, and so on, meaning it should never actually arrive. Of course, we know arrows hit their marks in real life, but in the quantum realm, something eerily similar happens when you watch a system too closely. Here's how it works. Quantum particles exist in a fog of probabilities until measured, at which point they pick a state. But if you bombard a particle with constant observations, say, checking its energy level over and over, it gets stuck in its initial state like a deer frozen in headlights. The particles don't have time to evolve naturally between measurements, effectively halting their quantum evolution. It's as if flipping a light switch on and off rapidly keeps the room perpetually bright, never allowing darkness to settle in. Experimental proof came in the 1990s when physicists trapped beryllium ions in electromagnetic fields. By zapping the ions with laser pulses at precise intervals, they prevented the particles from decaying, essentially using observation to suspend their natural quantum decay. The implications: if you could observe a radioactive atom non-stop, you might theoretically prevent it from ever decaying. But here's the twist: this isn't just about subatomic oddities. Some theorists speculate that consciousness itself could play a role. If our observations shape quantum reality, could a universe without observers remain frozen in an undecided state? It's a chilling thought, one that blurs the line between physics and philosophy, suggesting that time's flow might not be a cosmic constant, but a fragile dance between what's seen and unseen. So next time you glance at a clock, consider this. Even the act of watching might be bending time's fabric in ways we're only beginning to fathom. Could your body be hiding microscopic time crystals quietly ticking away inside your cells? Far from science fiction, there's growing evidence that some biological processes might mimic the eerie behavior of these strange quantum structures. Take circadian rhythms, the internal clocks that govern everything from your sleep cycle to hormone release. These rhythms don't just respond to external cues like sunlight. They persist even in total darkness, oscillating with near-perfect regularity, much like a time crystal's endless pulse. What if evolution stumbled upon quantum timekeeping long before physicists dreamed it up? The plot thickens when we peer into brain cells. Microtubules, tiny protein tubes forming the skeleton of neurons, have sparked wild theories since the 1980s, when physicist Roger Penrose suggested they might harness quantum effects to generate consciousness. Recent experiments reveal these structures can sustain rhythmic electrical patterns at specific frequencies, even when isolated from cellular energy sources. Some researchers speculate this could hint at a biological counterpart to time crystals, where molecular vibrations create self-sustaining loops of order. Imagine your thoughts being carried not just by chemical signals, but by microscopic metronomes keeping quantum time. Quantum biology takes this further, proposing that nature exploits quantum weirdness in ways we're only beginning to understand. Photosynthesis in plants shows near 100% energy transfer efficiency, a feat only explainable if light energy explores multiple molecular paths simultaneously, like a quantum time traveler testing all routes at once. Could similar effects govern how cells divide, how memories form, or even how we perceive the flow of time itself? The most tantalizing clue comes from fruit flies. In 2018, scientists found they could alter the insect's circadian clocks by manipulating quantum spin states in specific molecules, essentially rewriting biological timekeeping with quantum tools. If verified in humans, this could revolutionize medicine, hinting that our bodies don't just obey time's arrow but might dance to subtler quantum rhythms beneath the surface. So next time you yawn at dawn or feel the afternoon slump, consider you might not just be tracking the sun. Your cells could be orchestrating a symphony of microscopic time crystals playing the universe's strangest beat. What if nearly 3 centuries of history never actually happened? That's the audacious claim behind the phantom time hypothesis, a fringe theory suggesting that the years 614 through 911 were entirely fabricated, a grand conspiracy orchestrated by medieval rulers and the Catholic Church. According to this idea, Holy Roman Emperor Otto III, Pope Sylvester II, and Byzantine Emperor Constantine VII allegedly colluded to rewrite history, inserting 297 fictional years to legitimize their power. Birth certificates, royal lineages, even entire wars, all invented to create the illusion of continuity. It's a story so bold it makes the plot of the Da Vinci Code look tame. Proponents point to odd gaps in the archaeological record and inconsistencies in ancient dating systems. Why do some medieval artifacts seem suspiciously rare for such a long period? Why do historical accounts from this era feel strangely repetitive or mythologized? The theory's architects argue these aren't coincidences, they're evidence of a massive cover-up, a celestial sleight of hand where time itself was weaponized to control the narrative. But before you start questioning everything you learned in history class, let's turn to nature's own timekeepers, tree rings. Dendrochronology, the science of dating events by studying tree growth patterns, reveals uninterrupted sequences stretching back thousands of years. Oak samples from Europe, for example, show no missing rings corresponding to the phantom centuries. Even more damning, Chinese and Middle Eastern records from this period meticulously document astronomical events like solar eclipses and comet sightings that align perfectly with established timelines. If the years were fabricated, how did independent civilizations on opposite sides of the globe somehow coordinate their falsified star charts? The real charm of the phantom time hypothesis isn't its accuracy, it's the sheer audacity of the idea. In a world where we obsess over milliseconds on atomic clocks and nanoseconds in quantum experiments, here's a theory that throws out entire lifetimes with a wink. It's a reminder that time isn't just something we measure, it's something we construct, a story we tell ourselves to make sense of the chaos. And sometimes the wildest stories, even the debunked ones, reveal how fragile our grip on history really is. So while the phantom centuries might not hold up to scrutiny, they do something equally valuable. They make us wonder what other invisible threads hold the tapestry of time together. Step close to a black hole's event horizon, and time doesn't just slow down, it warps into something unrecognizable. At the singularity, the crushing gravity doesn't merely distort clocks, it shreds the very fabric of cause and effect until future becomes a direction as inescapable as down. Picture this: normally, time flows smoothly from past to future like an arrow in flight. But near a singularity, that arrow bends until it points irrevocably toward the center, as if space-time itself were a whirlpool dragging all possibilities into the drain. This is the universe's ultimate dead-end street, a place where timelines don't just curve, they snap. The gruesome process has a telling nickname: spaghettification. As you fall toward the singularity, the difference in gravity between your head and feet stretches you into a noodle-thin strand. But this isn't just physical stretching, it's temporal too. Time dilates so severely that your final moments, from an outside observer's perspective, would appear frozen at the event horizon forever. Yet for you, time keeps flowing toward that inevitable crunch. Roger Penrose captured this nightmare with his revolutionary diagrams, mapping how light cones, those markers of possible futures, tilt until all paths converge on the singularity. It's as if the black hole crumples spacetime like a piece of paper, folding the future into a single, inescapable point. Here's where physics gets truly bizarre. In Penrose's sketches, the singularity isn't just a location, it's a moment. A place where space and time switch roles, making radial distance behave like time. No matter how you twist or turn, every action propels you closer to the center just as relentlessly as aging pushes you through years. Even light, threading desperately sideways, gets reeled in like a fish on a line. The diagrams reveal something profoundly unsettling. Black holes don't just trap matter. They imprison time itself, locking it in a vault where later only means closer to the end. This cosmic censorship, as Penrose called it, hides the singularity behind an event horizon because what happens there defies the laws we know. Matter compresses to infinite density, space-time curvature runs off the charts, and Einstein's equations spit out nonsensical infinities. Some theories suggest quantum gravity might save the day, preventing true singularities with Planck-scale fuzziness. But until we crack that code, one thing's certain. In the belly of a black hole, time doesn't just end, it gets rewritten in a language we don't yet understand. A language where clocks don't tick but scream. Imagine waking up one day with all your memories intact only to realize you aren't a person at all, but a fleeting arrangement of atoms that randomly assembled into consciousness in the void of space. This isn't the plot of a sci-fi horror story. It's the chilling premise of the Boltzmann brain paradox, a thought experiment that pushes our understanding of time and reality to the breaking point. Named after physicist Ludwig Boltzmann, the idea suggests that in an infinitely old universe where particles bounce around randomly, it's statistically inevitable that a fully formed, self-aware mind could spontaneously emerge, complete with false memories of a past that never existed. The paradox hinges on entropy, the same force that dictates time's arrow. Over incomprehensible timescales, even the most improbable events like a hurricane assembling a Boeing 747 from scrap metal become certainties. In a universe where entropy reigns, a lone, thinking brain materializing from chaos isn't just possible, it's more likely than the orderly, structured cosmos we observe. After all, conjuring a single conscious moment requires far fewer particles than constructing billions of galaxies over billions of years. So why do we find ourselves in a universe teeming with history rather than as momentary flickers in the dark? Here's where time's arrow intervenes. For a Boltzmann brain to exist, entropy would need to momentarily decrease locally, creating order from disorder. While physics allows this statistically, such fluctuations are absurdly rare compared to the mundane march toward chaos. The odds of you being a Boltzmann brain, a transient glitch in the cosmic noise, are astronomically worse than winning the lottery every second of your life. The very fact that our memories align with a consistent, law-abiding universe suggests we're part of a much larger, stable system, not a fleeting accident. But the real kicker, the paradox, backfires on itself. If you truly were a Boltzmann brain, any evidence you used to reason about reality, including the laws of physics, could just be part of the illusion. It's a hall of mirrors with no exit where skepticism swallows its own tail. That's why most physicists dismiss the idea, not because it's impossible, but because it's unfalsifiable. A brain in a void could never prove it isn't one. The Boltzmann brain paradox isn't just a curiosity, it's a stress test for cosmology. If our theories of the universe's origins predict that Boltzmann brains should dominate over real minds, those theories might need reworking. Some researchers argue that the very existence of structured, enduring observers like us hints at a deeper truth, that time and entropy aren't accidents, but features woven into the fabric of reality from the start. So the next time you doubt your memories, take comfort. The sheer unlikelihood of being a Boltzmann brain might be the best proof that your past and your future are real. What if time could exist without anything changing? Imagine a universe frozen in place, no ticking clocks, no orbiting planets, not even the faintest vibration of atoms. Would time still flow, or would it vanish like a shadow when the light goes out? This puzzle has haunted philosophers and physicists for centuries, splitting them into two warring camps. On one side stood Isaac Newton, who declared time absolute, an invisible river that keeps flowing whether anything moves or not. On the other, Gottfried Leibniz fired back, arguing time is just a measure of change. No motion, no events, then time, he claimed, is nothing at all. Newton's vision paints time as a cosmic stage, indifferent to the actors upon it. Even if every star winked out and every particle stood still, the clockwork universe would keep ticking in the dark. His math treated time as its own dimension, separate from space, rigid and universal, a ruler for reality rather than part of it. This idea shaped physics for centuries, from predicting planetary orbits to launching satellites. Yet lurking in Newton's equations was a haunting question. If nothing ever changed, how would we know time was passing? Leibniz countered with relational time, an idea so radical it feels modern. To him, time wasn't a backdrop but a network of comparisons. The rhythm of a pendulum, the orbit of the moon, the decay of atoms, these weren't just ways to measure time, they defined it. Strip away all change and time loses meaning, like trying to measure wind in a vacuum. His view resonates eerily with Einstein's relativity, where time bends around moving objects and warps near massive ones. In a static universe, Einstein's equations suggest spacetime would crumple like an unwritten symphony. No events means no score for time to conduct. Modern physics amplifies the debate. Quantum mechanics treats particles as probability waves, frozen in superposition until observed. Some interpretations suggest time itself emerges from quantum entanglement, like a movie reel assembling from individual frames. Loop quantum gravity takes this further, proposing spacetime is granular, a woven tapestry where time is just the threading. In these frameworks, a changeless cosmos wouldn't just lack a clock, it might lack the very fabric clocks are made of. Yet black holes add a final twist. At their singularities, gravity grows so strong that mathematically, time and space swap roles. Falling inward, your future points irrevocably toward the center, not because time flows there, but because the direction itself becomes temporal. Here, even in perfect stillness, time doesn't vanish. It mutates into something stranger, a dimension where later isn't a moment but a location. So who's right? The answer might depend on where you stand literally. Newton's absolute time feels intuitive when planning a train schedule, but Leibniz's relational view mirrors how GPS satellites adjust for relativity's quirks. Perhaps time isn't one thing but many, a chameleon that shifts its meaning based on the questions we ask, or maybe like a shadow puppeteer, it only exists when something moves in the light. Either way, the next time you glance at a clock, remember, those ticking hands aren't just counting time, they might be helping to create it. The story of time doesn't have to end in darkness. While heat death paints a chilling portrait of eternal stillness, there's another possibility, one where the universe doesn't fade into silence but reboots itself in an endless cosmic encore. Enter the Big Bounce, a theory that twists the traditional Big Bang narrative into a loop. Instead of a one-time explosion, this model suggests our universe is just the latest act in an infinite cycle of expansion and contraction. Picture a celestial accordion. Space stretches outward until gravity finally wins, pulling everything back into a singularity so dense and hot that it triggers another bang. Time in this view isn't a straight line but a spiral, with each collapse erasing the past and birthing a brand new future. The math behind this is mind-bending. Loop quantum gravity, a leading framework for unifying relativity and quantum mechanics, replaces the Big Bang's infinite density with a quantum bounce. Imagine squeezing a spring, push hard enough and it recoils. Similarly, when the universe compresses beyond a certain point, quantum effects could reverse the collapse into an explosion. There's no before the bounce, just as there's no before the Big Bang. Time itself flips direction, like a record switching from play to rewind. The beauty. This could explain why our universe is so finely tuned for life. Each cycle might subtly tweak the laws of physics, meaning after enough rebounds, a universe like ours, with stable atoms and galaxies, was inevitable. But what if even the Big Bounce is too small scale? Eternal inflation takes the multiverse idea and runs with it, proposing that our universe is just one bubble in an infinite froth of expanding space. In this chaotic sea, new universes constantly bud off, each with its own laws of physics and its own arrow of time. Some might collapse instantly, others expand forever. Time's fate, then, isn't universal. While our bubble might face heat death, others could be cycling through bounces or birthing new dimensions we can't fathom. Yet for all its grandeur, eternal inflation can't shake off time's ultimate irony. Even in a multiverse, every bubble universe will eventually exhaust its usable energy. The result, a patchwork of cosmic graves, each a silent, frozen tableau where nothing changes and nothing ever will. Philosophers have a name for this, the problem of the edge. Whether time ends in ice or fire, the real haunting question isn't how it happens, but what it means. Does a universe without events still have time, or does time itself dissolve when there's no longer a before and after to measure? Perhaps the answer lies in perspective. To a hypothetical observer outside our universe, our entire timeline from Big Bang to heat death might appear static, like a finished sculpture. But for those of us inside, time's flow is the very fabric of experience. The universe's fate might be sealed, but here, now, time is the stage where every discovery, every moment of wonder unfolds. So while cosmologists debate whether time ends with a whimper or a bang, one truth remains: as long as there are minds to ponder it, time's story is still being written. Time isn't what we think it is. From the moment we first learn to read a clock, we're taught that seconds tick by the same for everyone, everywhere, but the universe laughs at that idea. We've seen how time bends like taffy near black holes, how astronauts return from space slightly younger than their Earth-bound twins, and how your head literally ages faster than your feet. We've wrestled with the block universe theory, where past, present, and future exist simultaneously like frames in a movie, and questioned whether now is even real, or just a fragile illusion stitched together by our brains. Think about the implications. If you could orbit a black hole, you might return to find civilizations risen and fallen in what felt like hours. GPS satellites, those unassuming beacons guiding your road trips, must account for Einstein's relativity just to keep you on the right highway. Even the simple act of looking at the stars is time travel. Those pinpricks of light are ancient messages from a past long gone. And let's not forget time crystals, those bizarre quantum structures that pulse endlessly without energy, or the Boltzmann brain paradox, which suggests your memories might be a cosmic accident. But here's the real kicker: all these mind-bending facts aren't just abstract curiosities. They shape everything from the technology in your pocket to the fate of the cosmos itself. Time's flexibility keeps the universe predictable, yet its mysteries hint at layers of reality we're only beginning to scratch. So which fact shattered your perception the hardest? Was it the holographic principle, suggesting our 3D world might be a projection, or the eerie possibility that wormholes could stitch together distant eras? Drop your thoughts in the comments. We're all time travelers here, piecing together the universe's greatest puzzle. And if you're hungry for more cosmic mysteries, hit subscribe. The next revelation is just a click away. After all, in a universe where time dances to its own tune, who knows what we'll uncover next?